Welcome to a video on importing and constructing signals in and for LTSpice. So, we sometimes need extra signals for our systems. So, simulations where you need to test a custom signal or that wants some strange signal as the input. The medical people for heart rates, and the people doing digital systems, DAC outputs, or data signals and streams. All of these systems still have analog front ends or analog back ends, and we still need to test this in simulation. So, in this video, I'm going to show you how to construct a signal in LTSpice, how to make a signal external and putting it into LT using Excel and a text editor. And then lastly, I'm going to show you how to construct a variable sawtooth and triangle wave and a variable block wave with a duty cycle using parameters. So, first to construct a signal in LTSpice, so I've gone ahead and made a little drawing of a signal that I want that's not necessarily available in LTSpice. So it's nice to draw yourself it beforehand so that you can see what you need and where. And I made myself a little test setup. Okay, so if you want to construct a signal like this, we go to the advanced options and say this PWL right here. Okay. And for this, we need to provide a time and a voltage, a time and a voltage, a time and a voltage. So for our signal, we are going to start off at 0. So at time 0, we have voltage 0. At the time of 1 millisecond, we are still going to have a voltage of 0. But from here on, it should steadily climb for 1 millisecond. So at 2 milliseconds, we should be at 2.5 volts. Right, and then it should remain 2.5 volts up until 3 milliseconds. Okay, so this is just a part of a signal. You have to describe the points. So if you need more points, click here and you can start to add them. Now, here at 3 milliseconds, there is a jump downwards to minus 2.5. If we double click, this jump cannot happen instantaneously, so you typically have to give it a time. So let's say 3.0000001 milliseconds, so that is a 1 nanosecond for the jump towards minus 2.5. And I'm jumping around between the blocks using tab. So it should remain minus 2.5 up until 4 milliseconds. And then it should decline towards 0 for the next millisecond. So at 5 milliseconds, we should be back at 0. And from there on, it would remain 0. So you can construct your signal like this. Say OK. OK, and it will throw out this very long description. So you can actually right click this to edit it if you want. So let's quickly run this and see if we actually construct our signal. And there we go. We built our own signal in LTSpice. Now, constructing signals like this could be really tedious to do, and there is better ways. and we're gonna go through them in the next couple of seconds. So first thing to remember is how to describe gradients and how to describe direct jumps like this. So the rest will be text file based. So I've set up a couple already, like this. The differentiate signal, it's for a practical, where you can describe a signal, and between these numbers there is a tab. So the first column you describe the time in seconds, and the second column you describe the time in volts. These can also be in the time column can be in millisecond format, like here, or nano, or pico, or micro, whatever you want. You can also use, I think I saw it, E notation. So 5 exponent 0, or whatever you need, -2. So you can describe the signal using millis or E notation, whatever form you want to. So you can put the signal that you're trying to describe in a text file. So you can create your text file, right click, new, and text document, rename it, and just edit. So the signal that we just did, if you want to describe this quickly, in notations, we had 0 for 0. At 1 milli, we were still at 0. At 2 milli, we had to go to 2.5. At 3 milli, we were still at 2.5. At 3.0001, we went to -2.5. At 4 milli, we were still at -2.5. And at 5 milli, we had to be back at 0. So there we quickly wrote the signal. Then to add one of these, you can just right click, say PWL file, browse, add it like this. Now wherever this is situated, you can run it. And I made a mistake. Okay. We open this. Oh, that is 3 seconds. That should be a milli. Okay. Run the simulation again. And we have exactly the same signal after I simulated it. Right. That is how to construct signals in LTSpice and construct it in text documents outside. Now I've already gone ahead and made some other files. So this one is for 200 milliseconds, if I remember correctly. And I constructed a strange waveform like this for a differentiator, and another waveform for an integrator. So you can construct literally any wave shape that you want. Here is a signal that I got from the internet. This is a very long signal. I think it's something like 10 seconds. So let's change this to 10 seconds. So for the medical people, you can have heartbeat inputs to a system. So literally anything that you can construct or find outside LT, put it in a text file and it's time and voltage or time and current. You can also put this in a current source. You can build any signal that you want. So let's go over to building a complex signal of our own. And for this, I'm going to use Excel. So let's say we want to construct a sync signal. Now, a sync signal is sine x divided by x, and we need to get this in some timed format if we want to get some data from it. Okay, so we make this sine omega t over omega t, and this can translate to sine 2 pi ft, and if we want to give it a specific amplitude, we can just multiply with a. Now this down here is what the sync signal looks like. So this signal starts off at the maximum amplitude and then oscillates downward. Okay, so we want to start at time 0, and Excel can't translate a divide by 0 because the sine x over x is going to be a divide by 0, but in maths this will go to the maximum amplitude. So we say that this is equal to our maximum amplitude here. That is 5. Okay, now this signal needs a frequency, it needs a time, and it needs an amplitude. Okay, frequency, amplitude, and a time step. So the first column here, we're going to say, okay, the previous time plus our time step. This is 1 millisecond. Okay, and we always want to use this block, which is describing our time step. So we make it $D$7. So if I copy this and paste it, it will count upwards. Okay, the second column here is our voltage data. Okay, so using dollar signs makes a fixed position. Anything else, if I put it in the equation, like this A2 with no dollars, it will just take the data in the same position as we move equation. So I need to build this equation now. So it's the amplitude. We say equals the amplitude. This is again a fixed position, $, multiplied by the sine, and this is a function, 2 times pi is a function, multiplied by the frequency. Again, the frequency is a fixed position, $, multiplied by time. Okay, so that is the top half. Divide by 2 times pi times frequency, and again the frequency is fixed, $, times time, and there is our first value. Okay, so we programmed our sync function. Now we can say copy these 2 columns, and let's say we want 2 seconds of data. 2 seconds, 1 millisecond steps, we need to go to 2001. back 2001, paste, and you will see that we have the data in 1 millisecond increments down to 2 seconds. So let's take all of this data upwards and we're going to copy it. And now we are going to go new text document. Let's call this sync 5 over 5 hertz sync, and we are just going to paste the data. See this last one, it's E notation. Save a document and we can close it down. Okay, so in our LTSpice we need to see this half of a signal. Okay, so let's open our LT and add our sync file. Okay, and this needs to be for 2 seconds, and let's run it. And there is half of our sync signal. So you can use a combination of tools as long as you can put the data in a text file to create the data that you want, and just put it in a file, add it to the voltage source, and there you go. Okay, let's say you want to build a triangle wave or a sawtooth or a square wave, and you want to use this pulse function, but you don't want to manipulate all of these every time if you want to change the frequency of it. So let's, for this example, work from 5 volts to minus 5 volts. Right. So for triangles and sawtooths, everything is in the rise times. Okay, so let's call this T1 and put it in curly brackets. The fall time, let's call this T2, and the time on, let's call this T. No, sorry, that should be in period. The time on, if we're talking about triangles and sawtooths, that should be 0. Okay, so we have created 3 parameters to work with. Right, so we want to be able to work with frequencies. So let's say dot parameter f is equal to 1 kilohertz. So we can define our frequency, and now we need to create stuff for our T1 and T2. Okay, so T1, let's start with a triangle wave. Okay, so the rise time should be half of the frequency time. So this should be 1 divided by 2 times f. Right? And T2 should also be 1 over 2 times f, and T is T1 plus T2. So now we have one place where we can change the frequency, and the rest of the parameters here will be calculated. And calculations like this is done before the simulation. So if we run this for 10 milliseconds, we should have our sawtooth. So 1 millisecond to 2 milliseconds, so it repeats. 1 over 1 millisecond is 1 kilohertz. So here is our 1 kilohertz triangle wave. So if we change this parameter to 5 kilohertz, there is our 5 kilohertz triangle wave. So by quickly defining the variables and understanding what the waveform should look like, you can define using the times your waveform. Okay, sawtooths. Sawtooth, one of the sides is very sharp and the other side is sloping. So we can say that T1 is just 1 over F. And T2 is 1 nanosecond long. And we can run this, and now we have a sawtooth. And you can adjust the frequency just like you want. You can still adjust the voltages just like you want, and it will calculate everything beforehand and give you your waveform. If you want the sawtooth to be in a different direction, just swap the positions of T1 and T2. And it will go the other way. There we go. Okay, so there is an easy way to create sawtooths and triangle waves, and you don't only have to adjust the frequency to make up your signal. So, what about a block wave with a duty cycle? So, a block wave with the duty cycle, let's say we need to make our rises and falls 1 nanosecond each. Our time on is going to be defined by our duty. So let's make this T1 in curly brackets. And our period is time, still time T. Okay. Right. So this second parameter T2, we can make our duty, and let's say we want a duty of 0.5 to begin with. Our parameter T here is equal to our 1 over F. And our parameter T1, our on time, should be T times D so 1 minus D. Right. Let's run this and see what happens. So there is our block wave with a 50% duty cycle. Let's make this 0.1. Now it's only on for 10% of a cycle. And make this 0.8. It's on for 80% of the time. So this D should be between 0 and 1. If we make this a 1, then our signal will be on continuously. So this is except these 1 nanosecond spikes that you're going to get. This should be nice for people that wants to test systems where you have different duty cycles and want to do them one by one on different ratios. So you can build your duty cycle, set the duty, set the frequency, without having to go and adjust this pulse parameter continuously and having to remember what value do I need to manipulate now. So that's all that I have for today on building signals using pulses. You can make variable using parameters and building and importing signals to LTSpice. Thank you for watching.